Hello, just testing, okay. Well, good evening, everyone. My name is Evelyn Miralles. I am the Associate Vice President for Strategic Information Initiatives and Technology at the University of Houston Clear Lake. I am actually delighted to be here and to see everyone tonight, and I'm honored to share with you this very special evening. Every October at the University of Houston Clear Lake, we celebrate the Spirit Week. It is a week filled with events and activities aimed at the school spirit and campus pride to promote education. There are many programs happening throughout the week. There will be plenty of opportunities for you to connect with others and show your school spirit. Please do so. The University of Houston Clear Lake has become a cornerstone of higher education in Texas. Since opening its door in 1974 to support NASA activities, advancing knowledge in space exploration, the university has awarded more than 75,000 degrees, each resulting in expanding employment prospects, brighter futures, and changing lives. One of those lives is my own. I am an alumna. I graduated from the University of Houston Clear Lake with a bachelor's degree in Computer Information Systems and an MBA in Management of Technologies. And then I went to work at NASA Johnson Space Center for over 27 years, helping to train astronauts for one of the most difficult jobs in the world as a spacewalker, and helping to pioneer a unique technology, virtual reality. I supported all of the space shuttle and space station missions since 1993. That was about 4 to 7 missions a year, sending our astronauts to outer space. It is my privilege to welcome tonight our guest VIP speaker, also an UHCL alum, Dr. Greg Chamitoff. An engineer and former NASA astronaut, he obtained a Bachelor of Science in Electrical Engineering from California Polytechnic State University in 1984. He went on and obtained his Master of Science in Aeronautic and Engineering from California Institute of Technology in 1985. Then he went on to get his PhD in Aeronautics and Astronautics from Massachusetts Institute of Technology in 1992. In 1995, he joined the Mission Operations Directorate at NASA Johnson Space Center as an engineer, where he developed software applications for spacecraft altitude control, monitoring, prediction, analysis, and maneuver optimization. Most memorable for us, in 2002, Dr. Chamitoff obtained his Master of Science in Physical Science, which is a space science, from the University of Houston Clear Lake. He was elected by NASA for the astronaut class of 1998, qualified for flight assignment as a mission specialist in 2000. He launched to space in 2008 on board the Space Shuttle mission STS-124. He then returned home to Earth in STS-126 mission, completing a tour that lasted 6 months while helping build the International Space Station. That is 6 months living aboard the ISS, space station, working across expeditions 17 and 18. Later on, Dr. Chamitoff served as a mission specialist on STS-134 in 2011, which was the penultimate space shuttle mission, during which he made 2 important spacewalks, the last one of which completed the construction of the space station. Dr. Chamitoff had logged more than 198 days in space, and I was there to see it. He's currently happily serving as a professor of engineering practices at the University of Texas A&M. Right now, what we're going to do is I'm going to talk about what we're here in the lecture to do. We're going to talk about training astronauts for space travel virtually, And I'm going to start giving you kind of the background of the technology and how we develop the technology for space training. And following after will be Dr. Chamitoff will give his talk, his presentation. So space training, what was the need for virtual reality? Really the need came about start doing a spacewalk when we decided that we were going to build a space station. It became immediately a concern that we were going to do a lot of those, and we needed something else to train the astronauts with. So we used to, this is the way that we train the astronauts with mock-ups, and we train them for spacewalks and robotics operation. But anything can happen, anything can go wrong in this environment. So it was very time-consuming to reconfigure and very costly. So we also use weightless environment training to train the astronauts. We do that in the NBL, Neurobuoyancy Lab, at the moment. But there was a mission, the Hubble Space Telescope mission, where we decided to start utilizing the VR technology in order to train the astronauts for that spacewalk to repair the Hubble Space Telescope in 1993. And that's exactly what we did. We put together a system that contains graphics, real-time simulations, and the helmets that we had in that time. And we built that simulation in order to repair the Hubble. We needed these three components. This is the important components in the beginning, obviously, of this VR system, and the input devices were very important to have. This is what NASA was working on in 1960s, and then what we got now in 2018, right? So we worked with the astronauts back then, going back to the Hubble Space Telescope time in 1993. This was about 1993. We have all the astronauts. I was there putting together all the graphics and the configuration to allow them to train for that scenario, repairing the Hubble Space Telescope. That was STS-61. So, and you see the astronaut riding back with one of the helmets, early helmets. So we used, for the first time, VR for space training for this repair. And this is our graphical, the way it used to be, the graphic and the resolution of that system at the time. So this was also a little bit of the history of how we went through the different systems. And I was there through all of them, between designing, getting helmets that were already built, and then kind of massaging that into something that it can integrate with our system. So it was very intense work in integrating those helmets. And here, this is one of the latest in 2010. And then after this, obviously, we have the commercial helmets. So that was kind of the progression. So VR, virtual reality, came to life throughout the beginning in 1993 and beyond, where the technology started to get better little by little. I mean, it took some time to integrate all the pieces and maintain everything in order to make it possible for continuous space training. So early on, our lab, and where I used to work at NASA, we used it for space training and to actually provide the capability of spatial awareness for astronauts that were going to be endeavoring and doing spacewalks. So VR provided that immersive environment where they can see themselves like they're outside the vehicle. And this is something incredible because if you think of, we used to have the shuttle. It's very small, and you can kind of visualize it. Even if you fly there, right, physically, it's an airplane. But if we decided to build a space station, which is extremely big, how do you visualize that over time as you're building it? So early on at NASA, we knew that this was going to happen. So we started thinking about these technologies and these graphical technologies to project how it was going to look like. So this has been the power of VR, being able to visualize the environment before you actually build it. So VR is a computer-generated immersive environment presented to the user as real. That's what it is. Again, it took a lot of time and many, many years to actually build the full space station, for example, because it took so many pieces as we went along for real, and you build it for real. But in between all those times, we were improving the technology, the VR technology. And if you think of it, in 1993, 1994, nobody was using VR. It was basically unknown. I think I heard somebody said something about that about 50% of the population today knows what is VR in the world. I was reading that someplace, which is kind of fascinating. So how many more will we have in about another year or two? It's moving pretty fast. But in our time, if you think of when we were at NASA doing this, nobody knew what was that. And nobody had an idea. And we were actually training astronauts doing this. So this is the graphic software that we have, that we built actually throughout the years. And it's funny to know this graphical representation, this graphic engine is called, because it's basically rendering that scene synthetically in real time. We built it at NASA. It was in-house, which is something also memorable, because there was nothing, when we started building this, there was nothing in the market that we can simulate. So NASA, we had to do it. NASA and the contractors, we have to actually build that to create the visualization of the space station, of the shuttle first, and then the space station. So this is actually arcade, because right now with the computer power, we can do more than maybe 10 million, 15 million polygons. So that's a lot of rendering power on a machine for graphical representation. So now this is a little bit of the activity that I used to be part of. Obviously, it's a group of trainers and everybody coming together with two astronauts in the back, getting ready to put on their helmets and to simulate a spacewalk. And this was also very important because it will allow also the participation of all the crew members, meaning crew members that were doing robotics operation and the ones doing spacewalking. And we could rehearse that at the same time, simultaneously in the same space. So imagine being immersed in the same space, looking at the same thing graphically, synthetically, and being able to communicate. That wasn't really that possible then, because you couldn't do it underwater. I mean, it was you have other constraints. You're doing other physical things underwater, and the communication is different. But here, you could actually rehearse the activity much more easily with the graphics, and we can reconfigure it and do it over and over again very quickly. So we learned a lot through all those times, and we realized that we were going to have this major training operations going as spacewalking. We did a lot of that activity. We did the Simplify A for AVA Rescue, is that safer backpack that the astronauts use to actually fly back to the station if they get detached at any time. And we have done that training in VR. We do a lot of robotic operation using virtual reality as well. Hey, hello. Also, we do what is called zero-G mass handling training, which is basically simulate that you're moving a mass in a space. So you use your helmet, you map the graphical configuration to a tangible, something that you can hold, a robot, and then you can move it and simulate that you're actually moving that piece of equipment. And procedure development, which is always useful. You can always see in 3D space, what is the activity that a spacewalker will do, and you can transfer them and move them around the space station graphically. So that was very powerful. So Simplify A for AVA Rescue, like I mentioned before, that's actually me trying to train actually Christina Cook, which she's in the space station right now. So before she left, which is going to be there for a year, we were training her. And this is before I actually came to work for the University of Houston Clear Lake, which, I started working here at the university 5 months ago. So before I was doing this for a living, right? So, and this is very memorable times for me. It was one of the last, trainings that I was doing, and that I was helping and supporting. And we have requirements like everything. Then we integrate all the components that we needed to move for her or for the mission and the specific configuration of that mission. And then we always test, constantly testing. So this is a process that I always tell, a lot of students or, and as I mentor some of the new engineers, about build your requirements and find the solution. What is the problem to solve? And then also the integration, you take a lot of time there, and you always test it constantly. It never ends. So we also have like I mentioned before, the robotics operations. So you see astronauts here. They are handling the robotic maneuvering in front of this mock-up that simulates a robotic mock-up of the same thing that you have in the space station. And then outside, kind of the representation of what they're looking at in terms of graphics. And then I have another here, part of the spatial awareness again. This is so important. This is Nicole Mann. She will be going to space as a commercial spaceflight. And I can't remember if it's a Starliner or a SpaceX Dragon, but she will be going into space probably next year or so. And we were training her into spatial awareness. What it feels like, what she sees outside, getting outside, doing a spacewalk or visualizing the space station from the outside. And I was, letting her train that and safer too. Then also, what I told you before, the zero-G mass handling. This is a very unique robot and setup. This is the only one in the world, really, that does that. And we have it right there at NASA. And it's basically what you see in the back is an astronaut holding this robot that if what she sees in the helmet is actually the mock-up of the items they're actually moving. She's actually moving. So she can move this in 6 degrees of freedom. She can rotate it and move it back and forth. So they can feel how it is to move a mass in zero-G, which is really difficult and different when you also have gloves that are pressurized and then you're orbiting the Earth, and so all the orbital dynamics gets involved, and it's complicated because and also where the center of mass of that mock-up is, or that piece of equipment that you're moving, is very important because it will do many different things and move differently depending where the center of mass is. So we needed to train the astronauts in that feel and touch that they don't get underwater, because underwater we have what? We have the dragging of the water. So the sensation is different than just moving something in a space. So this scenario gave them that momentum, that finesse, as they were going to move things in zero-G. And that's right here is actually a realistic representation. It was a training going on with the astronauts and one of the trainers, and we're supporting it. And you see the representation of the graphical and the mock-up being moved right there. So now procedure and review and development is very important. I think that humans, we all learn in actually 3D, our space. I think we learn better. We through time we decided that we were going to learn by 2D environment. But really, looking at procedures in a 3D environment, especially as complex as a space station, is much more powerful. So the tool that we built for, the graphics tool that we built for VR, actually allow also for the trainers and us and everybody to utilize it for procedure development of what was going to happen in the space station. Robotics operation, any configuration, we could do that real time with the graphics much more efficiently. So we always have lots of people coming together to actually build that. those procedures over and over. But it's a tool that it's a tool that we built in our facility, but then eventually in 2000, that was one of my jobs, was to actually make it portable. So we make that same tool portable, and then we send it to the space shuttle, and then obviously to space station. It just went on after that. So this is another interesting solution, and we're going to call innovation from our lab. It's called the laptop on the head. This was the first virtual reality in space for training. And we built it by utilizing a laptop that is running our graphics. We just split the image in two, and then we decided to just put some optics, like you see him doing, and we just created VR in space. And why we did it that way is because there wasn't any helmet then. There was none. 2000 and this one, we started working on this in 2010, half of 2010. It took us about a year and a half to build that, get it done, and certify for space, because to certify anything for space takes time. So we did that with this laptop on the head, which was pretty cool, and so we created the first VR in space. But of course, it wasn't easy to use because anything that is in your head, and you have the keyboard, and there was many constraints and things that we had to do, but it was really innovative. I mean, it was pretty, people are, oh my God, you really, they actually rehearsed their spacewalk refresh training, what we call it, in space with this. So that's why you see him smiling, because it was the first photograph with that. So that's memorable. Of course, then we went on again with Christina Cook. She's the same astronaut that is in space right now. And we sent a new helmet to space. We updated that system with a new helmet that is a commercial helmet. And we did that in 2018. So we went from innovating that first VR, into this updated version of VR for training. So, and every astronaut actually, they use it before they do the spacewalk. Is actually a checklist. I mean, they have to do it, and they rehearse the whole spacewalk virtually before they do it. So, and probably Greg can tell you a lot more about that. So, very quickly, just to give you the history of virtual reality for training. I mean, these are some of the dates. Obviously, the most important is when the first VR development was done in 1992. And then also we use it for the Hubble Space Telescope repair in 1993. And then we started integrating this astronaut training with VR in 1994 with the VR Simplify for AVA Rescue, or it's called SAFER. And obviously it go on until the last in 2018 when we did the updated version of the VR with the commercial helmet. It's called the Oculus VRT on board. So. Now, talk a little bit about some extra work that I was doing, that we were doing, is obviously creating more opportunities for developing VR, but now to simulate the inside of the vehicle. And why? Because now then we're going into the era of creating habitats, whether we're going to the moon, whether we are going to create new modules. So why don't we use VR for design and development? And I know Greg has some more information about that. And this will be the incredible, fascinating, time for VR to use as a tool for those purposes. And you're going to see some of that in Greg's presentation. So we were doing some testing back then when I was a couple of months ago at NASA. And also about AR, augmented reality. And I'm going to touch a little bit of this, even though it's beyond, right? Virtual reality is basically a fully simulated environment, all synthetic. It's all graphics. There is nothing real there. But when we have AR, it's basically augmenting our real world with pieces that are synthetic. So we can augment it, and we can use helmets for that. But the helmets, you still will have to see the environment. So there is a lot going on in this area. And NASA has been working for some time now developing procedures and to actually do repair or maintenance with AR. And again, you'll hear probably a little bit more about that. And this is something that is a very incredible, technology that is just growing. And it's being tested in different industries right now, not only in space, but other industries. So now this is also a pretty good tool that I was building before I left NASA. And it's basically, it's a VR, but it will be a VR tool where we will follow an astronaut as they're doing their spacewalk, and then you can see them, you can put your helmet yourself and follow what they're doing. And you can be basically with the astronaut. And then also, the astronaut can switch their view and have a real-time camera view of what they're actually doing, and you can also see that in the VR. So you can basically follow an astronaut, whether it's synthetically or graphically, either mode. And that's as easy as I can explain it tonight. But this is still in development. It's a prototype. It's being tested right now. But the actually use that I wanted to see in the future is for us to participate with an astronaut when they actually step on the surface of the moon, and we can follow them using VR. So imagine how awesome, how it will be for educators all over the world. Everywhere, I mean, everybody could actually be following an astronaut, stepping on the surface by just looking at his cameras or her cameras. This is something that is actually going to happen. I think it's just a matter of the stream data and all that, and helmets will become more available. But this is again being tested for spacewalk right now, and then we'll go beyond that, beyond LEO, low orbit. Now this is another great application I was working on. Is the augmented reality again. I utilize some of the helmets here is from a company called Magic Leap. There are several companies doing AR. This is just one of them, and I was testing the resolution and how much power can these glasses actually handle with the type of complex graphics that we run in our facility. So what I did with one engineer is just to replicate the training of actually repairing this spectrometer that you see in the back. That's the actually mock-up. So what you do with AR is augment that spectrometer with synthetic pieces so that the astronauts can train and identify the different pieces. So this is very unique, and it's more intensive. It takes more work, but this is something that is still in development because the technology is not. It's still getting better by the day. This is another shot of that, and here you see some of the synthetic or the items, the tags, so however you want to call it, that we built on top of the mock-up, and that's what the astronaut will see through the glasses. But they can still see the real world because this is augmented reality. So you can be training, having your trainer next to you, or having the other astronaut with you, talking about that, but you can see the environment and you can see these synthetic parts on top of the experiment, in this case, the spectrometer. This is going to become a very unique technology as we move into the future. Good part, like I said before, the astronaut could be moving around the whole space. And even though it's a mock-up, they could see like they are on space, and they can see the Earth. They can see, the whole mock-up to the spectrometer as part of the space station. And they loved it. They say, can we do this everywhere? I say, no, it's not that easy. But yeah, but it's pretty cool. Here I'm gonna play real quick, a quick montage that I have. I don't know if it's gonna play. Well, then the future. So this is what I see the future, and this is where we're going. I know many people say, oh, what? Yeah, but this is what we need to start thinking about. You know, in 10 years, 15 years from now, and you know, as we really get into the moon, I really see this. This is the future, exploring the moon and beyond with augmented realities, spatial computers. We have artificial intelligence that will be generating actually what we're looking at. So as we send astronauts and more astronauts into the planet and to the moon in this case, as we are mandated to be there by 2024, then this is, I think, what I look at in the future. So the spatial computer will be very powerful. Now, going beyond, you know, the combination of artificial intelligence with augmented reality will provide a full digital model of the spacecraft, updated in real time. So such a system will allow a crew to put on a VR visor and see real data overlay on top of the physical space. So this will be, I think, what we're gonna see in the future. And I'm so excited about, I'm sorry, this is caught. So excited about what is coming in this with this technology. Like I say, VR, very different to AR and mixed realities. But I believe, truly believe that all the mixed realities will be actually part of our lives more easily than what VR has been. And VR is a very mature technology right now, so we're just getting better in terms of helmets and the ergonomics of it. But AR and augmented mixed realities will be something that will be part of everybody's life, I think, like a phone. So having it on the moon and as we go beyond will be essential for the astronauts, will be very useful for the astronauts. So this is something that we definitely think of a lot at NASA. So. I think that concludes my part right now. So we're gonna take 5-minute breaks so we can change, and I'm gonna let Dr. Chamitoff then come in and have his presentation. Is that okay? Did tell me.
So
Just
how was
come.
the calibration process of like the VR? Was it based on like previous experiences from astronauts?
Yes.
Okay.
Yes.
That was
Some of that came to that. I mean, because they are the ones that know. So once they finish the mission, they will come back. We'll bring them over. They go into the training again, and then we'll test them again with them and say, so how did it feel? So they were the ones giving us the inputs. Like you saw in the beginning with the Hubble Space Telescope, that was memorable because it was the same astronauts actually helping us build that technology, because they knew they already have been out there, so they knew how that felt. So imagine early on when we were doing VR, you know, the power of the computer was lagging. It wasn't powerful enough, and we're like, okay, this is moving very slow. But in space, things move slow. So the astronaut would say, you know, it's okay if it's slow, if there is a lagging, but we are seeing the whole content visually. So for them, that was very powerful. So yes, all the inputs that we got usually came from the astronauts. And I can tell you, we have phone calls from space saying, oh my God, it looks just like the VR lab many times. So that was something that it was good to hear, that they felt comfortable with how they train.
And then my second question.
Yes.
Question is about AR. So I saw that on the pictures they were like wired AR glasses, right?
AR, yeah, wire, yes, that's a good question.
Did you use any wireless AR glasses, or still we're like in the wired?
Well, they're wireless. It's just that what they did in the AR augmented is that they separated the glasses, the optics, with the CPU. The power. So other glasses have it all in here, which is, that's what right now is the design.
Okay.
Either this gets smaller, powerful, you know, so all this is in development. It's still getting better. But that's why you have the wire, because the CPU is separated from your eyes, so that it's not in your face, and it's you know, it doesn't get warm, and et cetera, et cetera. Okay. That's why you see that wire, but it's wireless. Other than that, it was just all in that little pocket.
Okay.
So it's cool. It's pretty nice. It looks fantastic. That's for me one of the best AR that I've seen.
Yeah. It'll become a head-up display, right?
Yeah. It's pretty cool. Yes.
How long does it take to
Yes. How long? How exactly. That's how, yeah, 3 seconds.
So they don't have
That's
to
true.
more, it's like 50 or so.
It's a longer delay, yes.
4 minutes.
4 minutes.
So it depends on the orbital rate.
Mm-hmm. That's it, that's your answer.
Could that be improved or
I mean, unless you move Mars and you move the moon closer to the Earth. But that's a good question. I mean, but you know, that now with VR we can be there in a second. So, any other question?
We'll have more questions, so time for questions after.
Exactly. Yes. So yes. So well, we'll like I say, take it a 5-minute break and.
All right, thank you. Good evening, everybody. Thank you for having me. Thank you for the introduction earlier, Evelyn. It's really a pleasure to be here. I've known Evelyn for a very, very long time, working at NASA for many years. She had the coolest laboratory in the whole place, so we always really enjoyed spending time there. But even before I was an astronaut, I got to know Evelyn. I don't know if you remember this. You have to probably remind you, but we were working on graphic displays for all the international partners in the space station, and we wanted to have some kind of standard for a way of interacting with three-dimensional objects. Remember that? And it was very interesting culturally. It's not the same. Like, you think that when you drive a car, you turn left to go left, you turn right to go right. But do you think the Russians are going to think the same way? Not necessarily. So their Soyuz vehicle operates like a gunner sitting in the back, and when they want to shoot to the right, they move the back to the left. So to fly the Soyuz vehicle, you have to you go the opposite way. It's like you're moving the back end of the gun in order to fly. And some people like to have the God's eye view and manipulate the 3D environment, and others it's more intuitive to be inside the environment and move yourself around. And so we were trying to standardize this across all international countries working on the space station, and it wasn't easy. So that was a very interesting project, and this is before I was an astronaut, and then I got to play a lot in her lab, and that inspired me to do some things that I'm doing now at Texas A&M. So with that as a beginning here, let me just tell you that, let's see if I, oh, it's got to come up here. There, oh, hold on. It's a point, oh, there we go. Okay, I got it. Yep, okay. So I'm the director of the Astro Lab at Texas A&M right now. We have a couple other professors who work with me there. We got a lot of graduate students, undergraduates, who are all working on a lot of different space-related projects, but a lot of them are VR-related, and I'm going to eventually tell you about those today. But I sort of have two jobs tonight. I want to tell you a little bit about my journey and my mission, and then also tell you about virtual reality and how we are using that in space exploration. And we had a very, there's a lot of things that Evelyn brought up. I didn't realize a lot of history there that I didn't realize. And as she's talking, I'm thinking, yeah, that's very relevant to some of the things we're doing. These are some of the students in our lab. We also run a multidisciplinary design course. And so these are students from all across engineering and different departments. I think there's like something like 12 different departments represented on our team. Now we have over 50 people with about 10 students as kind of team leads. So a lot of people very engaged in this. It's very exciting for the students to work on this stuff. It's space. It's the latest technology. We're using game engine software. They're busy. When they're not working on designing something, they're playing the games. So, and I got to go home and install my second chapter of Star Wars too. So, so let me start kind of at the end, or maybe at the pinnacle. This is obviously a picture of the space station. This picture wouldn't exist if it wasn't for your lab, actually, because it was during a VR session. Two of us were out doing a spacewalk on the space station, and we climbed up to this point in VR, and I looked out over the space station. I said, "Oh my God, I got to bring a camera to capture this." So I knew we were going to be right there, right at the end of the mission, right at the end of the spacewalk, and took a look at that and go, this is the most hardware that's ever been in space at one time. It was the last assembly mission of the space station. It was STS-134, the last flight of Endeavour. And so we got to capture this. And so I brought the right lens out to capture that because I saw it in virtual reality before the mission. And the interesting thing for me is that I worked on the space station as a grad student when the station was nothing but PowerPoint slides. And now here it is, it's still a PowerPoint slide, but it's a PowerPoint slide of a real thing. So, so that's kind of the end point. I'm going to kind of go back to the very beginning. And this is the launch. Anyone can guess which launch this is? This is Apollo 11. And I was there. So we just celebrated the 50th anniversary, right? So this is 50 years ago. That's me 50 years ago. And when I saw that, I said, this is what I've got to do. This is what I want to do with my life. I told it to my parents, and they embarrassed me for the rest of my childhood by telling that to other people. But eventually it worked out. So let's go on. So I grew up in Montreal, and my dad was absolutely fascinated with the space program. He was an engineer, and I just remember vividly him saying, we saw this kind of a scene on TV, people in mission control, and he would say, who are those people? How did they get those jobs? That has to be the coolest job in the world. How do you get that job? And being in another country, even Canada, that's far enough away, it's just an impossibility, it seemed to him. And many, many years later, I worked in mission control, this is what it looks like now. And unfortunately, I never got to even give him a tour. So he passed away before I worked, right when I got this job, actually. And so he wasn't around for all my missions. So that's hard. But he inspired me, very much. And there's one other thing that he and I did together when I was this age. And there was two things on TV that were space related. There was the Apollo program going on, and then there was Star Trek, right? And Captain Kirk was jaunting all over the galaxy, having all these great adventures. And I wanted to do that too. And I thought, at that age, I thought, is it possible? Well, my dad went to school with William Shatner. My dad was at the same high school as Captain Kirk. Okay. And so he was telling me that, yeah, I know him. He went to my high school. When he's on the ship running around all over the galaxy, but I got it. This is great. I have to do this. Can you introduce me to? So I just have to tell you, because I did eventually get to talk to I got to meet him too, but I got to talk to him. I called him from the space station, and first thing I asked Captain Kirk, did anyone ever call you from space before? No, I was the first person to call Captain Kirk from outer space. And it was the weirdest thing. I was the one in space, and he was the one. I couldn't believe it. So, all right. All right, so skip ahead many years. This is the first launch of the space shuttle at 1981, January. I was a freshman in college at this time. And I thought, okay, I got to do something about this. I got to call NASA and figure out what, before I mess it up, I got to figure out what I got to do. And I spoke to a gentleman named Dwayne Ross at NASA. He was the manager of the astronaut selection office. And up until very recently, you could have called NASA and asked for the manager of the selection office, and you would have still spoken to Dwayne Ross. Many, many years later, 20 years later, when I interviewed and got hired, he was still there. And at this time, he told me, he told everybody the same thing, but it was very good advice, which is basically, don't plan your life around this. The probabilities are against you, but do things you're passionate about. And when you choose to do something, just do it to the best of your ability. So it's very good advice, and I tried to do that. I'm going to show you a couple of weird pictures now. This is me when I looked like when I called him. If you can figure out which one is me, I'm the one with the bad hair day. And we look like delinquents there, but it's two Eagle Scouts. We're not as bad as we look. It was but I did a lot of fun activities, things that I really enjoyed, but also things that were kind of relevant to possible astronaut training. And then something else happened when I graduated from college. So this is 1984 now. It turned out that Hoot Gibson was the graduation speaker. And that was just really cool for me. I got to meet him. It was the first time I'd met someone who had been in space, and he had gone to Cal Poly, where I went to school. And it was the first time I could see somebody who went, had followed similar footsteps and made it into space. And so suddenly there was a feeling like maybe this is, really a possibility. All right, fast forward again. This is the first day of astronaut training. We're in the 17th class of astronauts. I'm hiding in the back there somewhere. And when you take these pictures, you always have, a serious picture and then the goofy picture, right? So here's the goofy picture. Okay. All right, so astronaut training is a lot of fun and challenging. At the beginning is things like survival training, which is, part of it is, you may end up in that situation, but a lot of it has to do with teamwork, leadership, followership, self-care, under duress in a difficult environment. And so we do quite a few things like that. This is water survival training. This has to do with, we fly in the NASA T-38s, which I'll show you in a second, and this is in case you have to eject from a NASA T-38 and land in the water. Oh, that's weird. I'll be back up. Too many, maybe I've got in the way, I guess. Let's see. This is water survival training if you have to eject, have to escape from the shuttle before the shuttle could land, if the shuttle couldn't make it to the runway. Inside, these backpacks, we have not only a parachute, but a life raft and, a lot of equipment. So we practice with that. And then, the T-38 itself. And this is a very important part of our training because, as you can imagine, and we were talking about VR simulation here today, a lot of our training is simulated. And the great thing about a simulator is you can destroy things and then hit reset, and just go right back to it again. In real life, you can't do that. And so it's very important that we have some training that's real world, that has real world consequences. And the T-38 is very fast paced, decision making, communication, very, very quick thinking and tracking of things. And the decisions you make have real world consequences. And so this is a very important part of our spaceflight training. So we do some other training as well, and this now was because my class came in at a time when we were preparing for the International Space Station. So we were planning, for long duration space flight, and we wanted to have something which we ended up calling expedition training. And so we did a lot of things that are, similar to the survival training. They're teamwork, leadership, followership, stressful situations, long duration. See how well you can, handle yourself and working with others, for long periods of time. This is in northern Canada. It's run by the Canadian Army, and they drop us off in the woods by helicopter. This is 5 hours north of Edmonton in February. And the average temperature is 30 below, and they don't let us sleep. So they spend the whole time, we have a radio, that's all we have, and we have sleds and equipment. It's not a matter of starving to death or anything. It's simply you got a lot of equipment, and you have to drag it around on sleds, and you set up your camp, and it's 2 o'clock in the morning, and you're just about to get a nap, and but they're hiding in the woods and watching you with scopes, and they see that you got your camp set up, and so they call you. Okay, take down the camp, move to these coordinates, and they just do that to you the whole week, and so it's constant frustration with what they're asking you to do, and then things happen, people get hurt. Actually, somebody broke a leg during this training, and had to be evacuated. But it's constant duress, and then, in those temperatures, you have physical problems you start running into. But one guy on our trip was a very, very funny guy from New York, and he didn't have any camping experience. And he's a hilarious guy, and he got funnier when he got stressed. So we had a great trip. I don't know if I want to try to imitate him, but we had a great trip. The Russians do a similar type of training. This is winter survival, so if you land with the Soyuz capsule off course somewhere, Siberia, you have to survive until you're rescued. You practice everything from getting out of the Soyuz and then basically, surviving for a couple of days. The interesting thing about this picture, there's 2 of us, there's supposed to be 3. The third guy, notice we're standing next to a teepee. The Russians taught us how to build teepees. They're not the world's experts on building teepees. Don't ever ask a Russian to teach you how to build a teepee. So the third guy got carbon monoxide exposure from the fire inside the teepee because it wasn't ventilated properly. So we lost one, and we continued from there. Then there's Russian water survival training, and this also was kind of funny. And I've got to watch out how many stories I tell you because I'm going to run out of time. But this is you land in the water in the Soyuz. And you have to change from a spacesuit into a waterproof suit. And so you're wearing a spacesuit, you're sitting in the Soyuz. In the Soyuz, it's it's very small space. Your knees are about as close to your chest as you can get them and and breathe. And there's no moving from that position. That's the position you're in. You can climb out of the seat, maybe, and that's what you have to do. So we have to basically change out of the spacesuits, climb out of the spacesuits, all on top of each other. Put on many, many layers, and then finally this waterproof suit. Meanwhile, there's divers in the water shaking it to pretend that there's waves and to try to make you sick inside. It's about 2 hours of work, of just really, really hard work. You come out almost in heat exhaustion, and then you have to do this very delicate fall off the Soyuz, because if you push off, it could tip, and then water could go in and drown whoever's left inside the Soyuz. So they're grading you only on that last bit, how you fall off. But here's the thing, we can't figure out why you would ever do this, because because if you need to get out of the Soyuz in the middle of the ocean, it's because there's a fire or something, and in which case you don't have 2 hours to change costumes. So we can't figure out the reason other than it's some kind of, it's basically a hazing thing that the Russians want to put you through. And everybody has to do it. So, all right. And then, of course, there's training in all over the world, different countries, the simulators all around the country, and the spacewalk training, which we're going to get back to a little bit. This is a fantastic simulation that we do. It's not really a simulation, it's a real mission. This is the Aquarius habitat. It's off the coast of Florida, Key Largo, and 60 feet. It's mounted on the bottom. And we go down there and we can have a mission of a week or so. My mission was 9 days. And we do everything just like a real space station flight. We follow the same types of procedures. They're written the same way. The schedule's the same. We actually talk to mission control in Houston on the radio. Everything we do for the day is controlled by Houston. It's just like a flight director and a Capcom talking to us, on the space station. And we go out and we do spacewalks, which are dives. There's like a moon pool inside this habitat. One section has got, it's pressurized, of course, right? And so the water stays at a certain level in one section, and you go down in there and get your dive gear on and go on out. So we'll do like coral reef science and gather data, come back in, analyze it, upload the data, send it to mission control, the ground, and just practice everything like a real mission. And the neat thing about this is, first of all, it's a real environment. I mean, it's a real hazardous environment. It's called NEMO. It is on this NASA Extreme Environment Mission Operations, and you're in a real threatening environment, and you're dependent on life support equipment. And we conduct it like a real space mission. So it's a fantastic space. We call it a spaceflight analog. And okay, so that's kind of just a survey of some of the training that we do. These are some of the missions that I was on. So the first mission was STS-124, and this was bringing up the Japanese experiment module. It's an absolutely beautiful laboratory, the nicest, biggest one we have on the space station. I was the first Japanese astronaut to take care of it. I tried to say a few nice words to Japan in Japanese, but I was spending my time learning Russian, so it was difficult. I tried. I had a list of nice things I could say. And like, you guys did a good job today. Congratulations. But for 6 months, I was on the space station with these two guys, Sergey and Oleg. And the funny thing about the three of us is we were all rookies. So the space station was being operated for 6 months by 3 guys who had never been in space before, if you can believe that. Then there was a change of crew. Another Soyuz came up. Mike Fink came up with Yuri Lonchakov, and these, my Russian colleagues went back down, and I stayed up with them for the rest of part of Expedition 18. Then there was a shuttle flight that brought Sandy up, and I rotated with her and came down eventually. And this is another mission. This is 2011. This was the last flight of Endeavour, the one where we took that picture of the space station. And this was a mission to finish the assembly of the space station. So I'm going to show you a quick video from this mission, but there's a couple things before I do that. First, my last mission that I was on. I guess you guys recognize the bridge. Well, here I am in control of it. So actually what happened was NASA had a deal with Paramount. It was part of a STEM outreach thing, and NASA offered to fly a prop from the movies, the more recent movies. And so I had a phaser stashed away in my locker the whole time. And partway through the mission, I brought it out, went over to the commander, and said, "I'm taking over the ship." It was great. Anyway, we had fun with it. And eventually, I brought it back. Oh, come on, why is it doing that? It's probably because I'm in the way. I brought it back there. So I brought it back, and I got to go on the set and give it back to J.J. Abrams and hand it to him, and I got to speak to the bridge of the crew and tell them how Star Trek inspired me and how they were inspiring the next generation. And I handed him the phaser, and he was really appreciative, but I wouldn't let go of it because I really liked that phaser. So, all right. So my first mission, something happened at the beginning of the mission that was funny. You know, you can imagine there's so much redundancy on board the space station. You know, multiple solar panels, all kinds of backup channels for power. You know, computers that if they fail, other ones will take over. But there's one Russian toilet. And it had failed just before our launch. And so NASA, I wasn't sure in the last 3 or 4 weeks before going to space whether I was going to go or not, because NASA didn't want to leave a crew member on board the space station with a, you know, failed Russian toilet. And so actually it worked out really well. So it was like this. This is not the device, but this is a urine separator, and it was a device like that that had the problem. And there was redundancy. There was three separators. All of them had exactly the same problem. So on board, they had changed the separator out, went through all the spares. They all had the same problem. And so Russia very quickly made another spare. We got it on the shuttle flight, had to get it through customs and, you know, in the airport and everything. And we brought it up there. And so this little quick video here, if you listen carefully, you can tell that this is a plumber call, the beginning of the mission.
You might need one more
8
right.
inches.
Volume? Can we get some more volume?
0.09.
2 inches.
Thank you.
That was a great fly.
Can we get any more volume?
Discovery arriving.
That was amazing.
Okay.
Incredible. It's beautiful. Beautiful sight.
Yeah.
Wow.
I'll look for anything. Yep.
Hey, you guys looking for? Hey, you looking for a plumber? Hey! How you doing?
Okay, that's the most volume we got, but anyway, you heard it, I think, right? Okay, all right. So let me show you a video here now from that mission, a short video. It'll give you a sense of what it's like to be on one of these missions. This was STS-134, the last flight of Space Shuttle Endeavour. Okay, thank you. I have to say, the person I was arguing with about who's upside down, that's Mike Fink, and I flew with him on he's the one who came up on for Expedition 18 as commander. And so I had 6 weeks on the space station with him. I have to say it was one of the funnest times because I would usually sleep longer than him, and he would be coming through in the morning. And every single morning for those 6 weeks, the way I woke up was, "Hey, Greg, guess what? We're in space." That was how I woke up every morning. It was great. Okay, so I don't want to spend a lot of time on this. You have to forgive me because I want to talk about virtual reality. But obviously, we spend a lot of our time in space doing science. Earth science is a big part of that. I took over 20,000 photos myself, and we're studying all kinds of sites all around the world. That we're monitoring for the environment and changes in the environment. It's also a fantastic, platform for studying space science, for astronomy and space physics. It turned out that you showed a picture of the alpha magnetic spectrometer. This is the alpha magnetic spectrometer. We brought it up on our last mission. It's a $2 billion cosmic ray detector. 16 countries built this together over 10 years, and it's up there collecting millions of particles every day, cosmic ray particles, measuring basically their mass and then their energy, curving in this big magnet. So basically this studies matter and antimatter and is looking for the signs of dark energy. And there's some now it's been up there for a while, and there's some really neat papers that have come out from it. There's been enough measurements to have some actual indications that point in the direction of dark energy. So I just saw one of those the other day. So it's been really an amazing machine. And of course, we're doing tons of science inside. Sometimes, 75 experiments at a time are going on, all different fields. The really amazing thing is that what happens on microgravity is this extra variable, gravity, changing, has an effect on many, many things you just wouldn't imagine. Here we're used to gravity just being a fixed number. And as soon as you let it be a variable and change it, things in all kinds of subject areas change. So a couple of examples are here, but I'll just give you one. So this is salmonella. And there's over 50 genes in salmonella that behave differently in zero gravity for some reason. We don't know why, but they do. And we've been able to take advantage of that and develop a vaccine against salmonella and against other things now because of that property. And there's really not really an explanation for why the genes behave that way, but they do. Of course, combustion and fluid physics, all kinds of things, are different in zero gravity. And we do a lot of experience with materials and coatings and things to see what happens when they're exposed to the vacuum, the radiation environment. Robotics, and of course, human physiology, studying human physiology. How are we affected by being in zero gravity, and what are the countermeasures we need to figure out to be able to be up there longer and travel further. There's another category that I like to call engineering science, which is everything we put up there to try to do something. Every system we build, for example, a life support system, it's an experiment in itself. It's one of a kind thing, and we're putting it in a space environment, and we're discovering what's wrong with it. Why it doesn't work. It worked fine on the ground. It doesn't work in space, and there's some reason. And so we're experimenting with all the technology that we're putting in space. And so, for example, this is a carbon dioxide scrubber that I took that whole thing apart and put it all back together that day, down to every piece. And it was like a 9-hour job with 2 people. And we had to change out a bed that was never supposed to fail. And but we need this thing to work perfectly if we're going to go to Mars. We need to be able to design one that works perfectly and we can rely on it. And so this is the kind of thing that we're learning. This had to do with today's coffee and yesterday's coffee. Everybody's smiling. It had to do with recycling the coffee, right? And so, but it's funny because these guys are smiling because they brought up the urine processor and it's working. Mike is smiling because it's his urine that they're all drinking. And anyway, some robotics. Okay, so let me talk a little bit now, finally, about just switching gears now to spacewalk training and robotics and virtual reality. So as you know, and as Evelyn was describing, we do a lot of work in this neutral buoyancy lab in this pool. It's 40 feet deep and about 200 by 100 feet. The whole space station fits in there all folded up. The shuttle used to be in there as well. And it's a fantastic environment for testing everything that we do. I mean, we're in the real spacesuit. We've got all the tools and tethers that we're working with. The fact that we can make things neutrally buoyant makes it possible to simulate zero gravity. But it's not really the same as being in space, as you already heard Evelyn talk about, is that because there's drag in the water, and there's also buoyancy. There's weight and buoyancy, and if those are perfectly lined up, you float there. But if they're not lined up, there's a torque that you're having to deal with. And fighting that torque, if buoyancy is one way and gravity is another way, and they're not lined up, is really a struggle. And so there's a ton of things we do underwater that are very, very difficult, especially like if you're working on your side or upside down. There's a lot of things that are very hard to do. And not only that, it takes a huge team of doctors and divers and to set up the space station for what it's going to look like a year from now or whenever the mission, that particular spacewalk is going to be. And so there's a lot of things that we can do in virtual reality, which I'll say in a second. This is a picture of from that last spacewalk where we finished the assembly of the space station. And that's Mike Fink, the guy I've been talking about. It reflected in my visor right there. He took this picture, which was very lucky for me. But this picture is very helpful here because what I'm actually standing on is the robotic arm. I'm not standing on anything, and I'm not holding on to anything else. There's nothing behind me that would support me here. And we had to do some work right here in this area. The robotic arm is attached right there. It's a wide-angle lens, so it looks weird, but it's going up and back and then comes down behind me, and my feet are mounted on a boot plate on the robotic arm. And I had to go somewhere else on the space station. Someone inside the space station had to fly that robotic arm over to me. I had to mount myself to it and then have him fly me over to this work site, and that way I can be here working at this work site where I'm basically standing out in the air out in front of this truss. And this was absolutely impossible to train underwater. And for a bunch of reasons. But for one thing, just getting the coordination between the robotics and the EVA both happening at the same time, very difficult to set that up. The arm can't hold itself up in the air. It's in the water it can move, but it can't hold itself up, the mock-ups we have of the arm. It works in zero gravity, but not in 1G. And if part of the arm sticks up out of the water, it can't hold itself up. So it would never be able to even do this position that we needed to hold me in, let alone fly me over there, in and out of the pool and then back in or whatever. That would have been cool, but can't do it. But in the VR lab, we can totally simulate this entire thing. I can go over to the place on the space station where I need to get into the boot plate. My crewmate, his name is Box in this case, he's on the robotic arm and we're talking on the radio. And the thing that we can do that you were mentioning is we can practice the detailed coordination between each other. You can sort of imagine, I need to be able to say, take me that way. but where am I? I'm facing something, which is that toward the Earth? Is it toward the front of the space station? Is it my left? Is it the left of the robotic arm? So there's different reference frames. We got to talk in the same reference frames. I need to say, 1/2 meter station y-axis plus, and then he'll go, okay, I know what you want. But he'll have to put himself in the right reference frame to make that happen. So that coordination, that practice of working with each other, the verbal communication, moving the arm and not smashing into anything, we can do this for hours and hours and hours in virtual reality, and we can break things and then do it over again. And it doesn't take 50 people and doctors and the whole dive team, for us to practice that. We can do it endlessly with just the two of us, and maybe Evelyn, to help us set it all up for us. The other thing is, we're planning this for a spacewalk that's a year from now. The configuration of the space station right now is not like that. It's a different, we were building it at the time. So what's in the pool is different. So either you have to reconfigure everything in the whole pool to match, the day of the spacewalk that's planned, or in VR, you just load a different file, boom, and you got the right space station mock-up loaded with everything where it's supposed to be. This is very, very powerful, and that's how we used it. Okay, so and I kind of explained that, and oops, come on. A little bit forward again here. So, okay. This just so you've seen a lot of pictures in Evelyn's presentation, but these guys are just sort of getting a tour of the space station. But normally you can actually hand walk your way around and do your tasks. There's some other things that you can do here in VR that you can't do under in the pool very easily. As I mentioned, the space station is folded up to fit in the pool. Here the space station is in its full glory, laid out the way it's actually going to be. You can put yourself upside down and backwards underneath something, way out, in one part of the space station, and you can think about it like, okay, if I'm up here upside down and backwards, which way, and there's an emergency, which way is it back to the airlock? Is it that way? Is it that way? Once you're upside down and backwards, you have to think about it, and you can practice that, in virtual reality. You're learning your way around, basically, and you talked about some of the familiarization as well. The other thing is you can change the lighting, in VR. It's hard to do that in the pool and get the lighting conditions that you might have to deal with. So there's a lot of things like that. All right, so this basically, this work in VR and the fun I had doing this in the VR lab at NASA kind of got me going on a project here that we were working on at Texas A&M that I want to tell you about. So first I want to tell you what the project is, and then how we're using it to do things related to spaceflight. So it's called Spacecraft. How many of you know the game Minecraft? Okay, so think about Minecraft for adults, where the physics is right and everything works properly. Okay. I saw my kids playing Minecraft, with friends at it, and thought, gee, if people, who want to be involved in planning the future of humanity could collaborate like kids do in Minecraft from all over the world and build things and share them, that would be amazing. So that's kind of what we built with Spacecraft. All the physics and math are basically built in, and it is a model of the solar system, the planets, the physics, the environments, and then the models of anything you want to build go in that and then interact in that environment, with the environment and with each other. And then humans can jump into the environment and then interact with everything as well. So this is basically what it is. And I'll just go ahead here, if I can let me go ahead. So just a couple of points of what the vision is. So it's a collaboration platform, an engineering collaboration platform. It's a detailed model of the space and planetary environments. It's an interactive simulation. So it's not a simulation that just runs as a function of time. It's a simulation that runs based on what happens. Events happen, people interact with equipment, and stuff happens because of events. It's an event-driven simulation. Can be used for planning and testing humanity's future. In other words, mission design, mission evaluation, operational planning. And also it's a fantastic environment for training. I'll show you some examples. And also education, for getting kids engaged with space exploration. So some of the things that are, I keep getting double hits. Some of the things, oh, come on. I'm getting more than double hits, like 5 hits. Maybe I gotta have to be closer. Is that moving? Okay. So yeah, so very high fidelity models of the solar system. So if we have data, if the data is out there, it should be in this model, for planetary surfaces and so on. And then oh God, I'm really struggling with this remote. I could jump ahead multiple slides. Okay, so high fidelity physics and dynamics are in there. So this is a very high fidelity model of the Martian surface. It's really where the Curiosity rover is. And then the model of Curiosity is very accurate. And then the interaction with the friction and the wheels and the bogies, everything here is really high fidelity. So we can do things like that. The environment models have to be in there. So oceans, atmospheres, orbital mechanics, all those kind of things. Radiation, it should be the real solar system. So you put your vehicles, your models into the environment, and they interact with the real environment. And then we have a lot of different models already in there for things that we've been doing. For example, spacecraft and rovers, habitats, and lunar landers and things like that. That's the next one. So the idea is you don't necessarily build these things from scratch. You can grab one of the models that's already there, or users of this would basically look at the library of what other people have done and say, I want a robot. Here's one. Let me make it my robot by changing the appendages, changing the algorithms, and then just upload it back into the system. So the idea is it's a model sharing system for all the models that would be used for space operations. A good example would be if somebody designed a GPS constellation for the whole solar system. That would be a fantastic thing. We know we're going to need it, but there's no way to fund that right now. but you could put that into space, into this system. Everybody who's designing deep space missions could use it and keep improving it. And at the time when we're ready to build it, we know we have something in simulation that not only the designer but the rest of the world thinks is the right way to do it. So that's one of the things we're trying to do. And then models have both a physical characteristic as well as the algorithms that define them. So, for example, you can't see it here, but this spacecraft has got vision-based navigation on board. It's seeing these asteroids. This is a unusual, not a realistic simulation really, but it's seeing these asteroids, it's mapping them, and it's deciding based on that what it should do for its path planning to make sure it maneuvers through them and doesn't run into them. So real-time path planning with obstacle avoidance using vision-based navigation. So these are kind of things that we can build into the tools. And then human interaction in the simulation, so there can be multiple people. What I really want to do is imagine if 3 of us in this room who are in completely different locations could jump into the simulation in VR, be in the Martian base together. We see each other there, greet each other, open the airlock, walk out on Mars together, and then do some task, using some tools, interact with a robot or something, and evaluate a mission together. But that's what's coming, and that's what we're working on. You can also evaluate the human factors, of a system with something like this. And this is actually NASA's model of Orion. And for example, this EVA crew member could be looking at the handrails and where they are. Are they in a good place for being able to move themselves around on the outside of Orion, essentially? And also you talked about inside the habitat, inside the space station or habitat, designing things and evaluating them before you actually build it, and letting many people explore that and contribute to the design. This one, this is kind of to give you an example of interaction between models that we can do. So this looks simple, but it's a really high fidelity model of the physics, of the environment, of the orbital mechanics, and of the space station and the Soyuz vehicle. But what it's doing here is it's trying to redock at another docking port. But it's trying to do it in such a way that it doesn't fire its thrusters at the space station. It's actually looking at all the thruster plumes and the interaction of that with the space station and deciding on how it's going to do its maneuver in such a way to minimize the damage to the space station. So these are some of the things that that we can do. So those are here's a STEM education one. So this is just for fun in a way, but there's something important here. And so this is kind of like you can design a planet, change parameters. So for example, if you're looking at an exoplanet and its mass and it's the spectrum of the atmosphere and other properties, you can build maybe a likely version of the planet. And when we create a planet, we're not storing the data. We want to create this planet down to a pebble, and or let's say there's life on the planet, down to the leaf on a tree. But we don't want to store the whole planet, in memory. That's not what we're doing. So this planet, for example, where this guy is running around on, every detail of that planet is generated. It's generated on the fly based on what you see. So if you look this way, this gets generated, and that doesn't exist anymore. And if you turn back over here, this is regenerated from scratch instantly. So this is where we've gone in terms of the speed now, is that we can render this whole planet down to a pebble. So if you look at if there's a leaf on a tree, if this was here on in my view, and I turned away and I looked back and it was something else, it would be very disturbing. But it'll be exactly the same thing in the same place, even though it wasn't in memory anywhere. It was generated basically pseudo-randomly. And that's what you're looking at here. So anyway, but that's kind of for kids to be able to create planets and games and things like that. Okay, so I want to give you some examples of where we're using this now. I'm just going to bring this up. Some examples. I want to end with these 4 examples. And so what we're trying to do now is use this tool to plan space missions and evaluate mission designs, concepts. Look at human performance to do a task that we can simulate in virtual reality, and possibly train somebody to perform that task better using virtual reality. So I'm going to start with the first one. So this first one is it's a piloting task. So the student who did this kind of got carried away with the color of the sky. It's, but this is a rotating habitat. Okay, so this habitat is rotating to get artificial gravity, right? So when it's rotating, on the inside wall, you have the equivalent of gravity from the centripetal acceleration, right? So if you're standing right there with your head this way, you're going to feel force pushing you down to the wall. This is big, really big, like the structures in there that people could be in, for example. There's no way to simulate this. There's no way to do this in an aircraft or underwater. There's no way to build something other than a virtual reality and test something and test, designing anything for this or operating something in this environment without it building the real thing or virtual reality. Those are our two options. And what we did in this case was look at flying a quad rotor. You'll see. I guess I can show the simulation. It's flying a quad rotor along a path, and how hard that task is hard in this environment. And it has nothing to do with. There's no reason to fly a quad rotor in this environment. It's just a task. But the question is, does doing this in VR help someone learn how to do this task better? And that was the study. And it's a difficult task in this environment. If I was in the spinning habitat, let's say the habitat was spinning and going this way. If I threw a ball forward, it would be going faster than it needs to go to have the same gravity as me, and it would get pulled down. And if I threw it that way, it would be going too slow, and it would go up. And if I throw it this way or this way or this way or this way, things curve in weird directions. If I try to pour your coffee into another glass, I'd have to hold it sideways because it would go like this. It would move to the side as it fell. So it's a really weird environment. So flying the quad rotor is not so easy. That's why it's hard for the person to do it. And so the point was, can we design an interface that allows somebody to do a task? Can we look at different ways to do that task and build an interface different ways and decide which is the best one? And can we evaluate the human's performance doing it? And does VR help them perform it better than if they're not using VR? So this was done using VR, not using VR. So anyway, bottom line was using VR. The folks who were participants in the study were able to do a better job learning how to fly this thing, and so that kind of showed the value of VR as a teaching tool and an evaluation tool for human performance. So that was the idea. Okay, so this one a little shorter. This is an actual exercise piece of equipment from NASA. This is a prototype of a much smaller thing, which is like a rowing machine we're going to put up in space and use for exercise. And the idea is, can you get better adherence to the exercise protocol and get maybe better performance out of the crew members if they're in VR doing something interesting while they're doing the exercise. So we're going to basically, we're putting them on a boat on a river, and there'll be somebody sitting in front of them rowing that they're going to keep pace with, and another boat that they're racing against next to them. And so this is not finished yet, but the idea is to see, basically see if this is a useful enhancement to the exercise protocol. So this is something we're doing directly with NASA. And this is with the Mars Society. They have a habitat in Utah, and they practice Mars missions there. And so, the idea is these guys are dressed up as, they're dressed up in simulated spacesuits. Everything they do is like a real mission. They walk out of a habitat, an airlock. They go through a procedure. They put on a spacesuit. They're outside doing tasks and operate in a way that they think they would operate during a Mars mission. And they try to decide what's the best way to do this task or mission on Mars. So we're helping them by developing astronaut training. So they want to train people before they go to this mission, so they already know how to do many of the procedures in the same way we would train people to execute procedures before going to Mars for real, right? And so so here's an example of something we've done with them. So this is, you'll see in a second, there's kind of a procedure on a little iPad. You can click on steps and it'll show you the next step. But basically it's a mobile device with the procedure, and use it to guide you, and then you can go through the steps of putting on the spacesuit, working the airlock, grabbing the tools, basically follow the procedure. And we're looking at a whole suite of procedures with them on, to see how well we can train people with these procedures and how well they perform when they get to Mars, and then they do them without any training other than, what we've done in simulation in VR. So that's that. And this is the last one. And this very much relates to something Evelyn was talking about. So this is using a heads-up display. This is augmented reality now. We're doing this for a spacesuit display. One of the things that take the most time for us on the space station is working with procedures. And of course, all our tasks have procedures, so that makes sense. But following a procedure is like reading something that says find connector XY2713-J, and then find connector 227749722550. I'm not kidding you. really long names. And so you go and look for those connectors in the location where you're supposed to find them, and there's 100 connectors there. And so you're looking through, you look through, and you go back to the procedure and you read it again, and you go back to the area. So we spend a lot of time trying to read and do and follow a written procedure. And so, and you were kind of alluding to this, since if we could have tools that could guide us directly, so in a heads-up display, an AI that basically recognizes, when it sees that connector, it recognizes it and highlights it for you, or it changes its color. And verbal instructions tell you, your next step is get that connector connected to this one, and have that kind of automatic guidance. So for EVAs, we do this with a person right now. There's a person inside the space station, and the EVA crew member's outside, and they can't carry a procedure with them, a piece of paper or a laptop, right? So they have to be told what to do every step of the way. And a lot of times they're not ready, for the next information, because they're busy concentrating on something. So there's a lot of, wait, okay, what was that? What did you say? And it's very slow in communication. And the person inside is like following the procedures for two people, but it's hard to see what they're doing. So it's very difficult. And we also have sometimes the person on the ground in mission control doing that. So more people involved, it's very cumbersome, and it's slow going. So anyway, this is something that applies not only to EVA, as you mentioned, inside the space station, any task. It's used, now it's being looked at, for maintenance activities and any kind of procedure to try to build that kind of an interface that somebody can use to automatically guide them. And one of the studies we're doing here is really looking at how do you interface with an AI like that? Do you with the gloves on and the suit, it's very hard to push buttons or do very detailed tasks. So is it a voice interaction? Do you stare at something? So is it eye tracking? Is it voice? Is it can you use a gesture? Can I go like this and that means go to the next step? Can I go like this and it means go back a step? So we're looking at the interaction of the crew, with those kind of options for interacting with an AI that is built into a heads-up display. So I want to talk to you about this further because I didn't realize NASA we might be able to use what we've been working on. So anyway, it's very exciting stuff. I want to end here now. So you've heard about the Artemis mission, hopefully. This is what's happening now. You mentioned it. Trying to get the first woman and the next man on the moon by 2024. That's the plan. We'll see if we can actually do it. And what we're trying to do in relation to this is we're trying to build the Artemis mission basically in VR, so that it's possible to practice everything we're going to do on the mission before we actually do it. To evaluate it, and then once we decide on the best, in terms of if it's a design, we can evaluate the design. If it's an operation, we can try the operation and see if that's the best way to do it. And then we can train people to do it before actually getting there. So this is what we're trying to do. We're at the beginning of this, and I just want to show you one thing because I think it's cool, and it's all I can show you so far. But this is our highest fidelity version of the moon, and I've never seen anything this high fidelity before. But this is the moon. Now it's not in VR. If you were in VR, you could stand on the moon and stare at the Earth, and be in a real place on the moon, which is just incredible, and probably the closest I'm going to ever get. So I'm looking forward to that. But the other thing we talked about was where this is really going is things like telepresence, where you could be in VR and you're either remotely seeing what someone else is doing or what a robot is doing that you're controlling, whether it's on the moon or one of the moons of Saturn or something like that. But I think that's really where things are headed. So I'm going to stop there. Thank you guys very much for being here tonight, for your attention. And thank you. I have, for your kids or whatever, if you want them, I have some signed pictures up here if you want them. And we can answer any questions that you guys want to ask now. Yeah. Come on over here. You're the expert, so I need you here.
I'll be back here. Any questions?
Yeah.
Yeah, thank you for the presentation. One question I have is with VR simulation, do you have the haptic feedback too or not?
Good question.
Not yet. Not yet. We can't afford it. That's the only reason.
That's what
Yeah.
I was going to say.
Yeah.
I think it's very computation expensive.
Yeah.
You can bet that. So, but in your experience, how important is that to the mission? Like what do you haptic?
I think it's going to be important. Like we're looking at, there's some other studies we're doing. One of them is comparing using VR in different situations, whether it's, for example, a therapeutic VR session for a crew member, or practicing for a real task, or a game-like thing, and in these things, there's some other, I don't mean, not haptic in the sense of necessarily, being able to touch things, but there's some new devices coming out where you can smell and you can feel air, and so there's adapters that can go on the mask that will give you odors and wind and temperature, and some of these things could really add an amazing dimension to it. Water mist, and so that could really add, like, so for example, if you're doing that rowing machine and you're filling the spray of the water, you could really, and a little bit of breeze, that would really add a lot.
We did some experiments when we were in the VR lab, adding haptics, like if you touch, you were close to a station and you bump on it. For some reason, what the instruments that we have, the sensors we have, they were not working well. So we decided to leave it, and since we're in operations, we had to train it. It was difficult to do R&D, research and development, which is the other side of it. That's why I love what they're doing at the university, because you start experimenting with all these possibilities. But anytime you add another sense into that environment, it makes it really, more real.
Have you done the void by any chance? Has anybody done the void in here?
Oh yeah, that's fantastic.
You've done it?
Yeah.
Yeah. So if you ever see this, you have to do it. It's a Star Wars thing.
Oh.
But you're in VR, in VR you see this table here, but you reach out and it's there, and there's a gun on the wall, and you reach out and you pick it up and you're holding it, and you can touch a little knob on it and it's there, and you're completely immersed. You feel the heat from that you should feel because you're near something hot, and it's completely, they set it up, in a special place so that these things happen physically.
Yeah, that's
really
an expensive setup.
Yeah,
It's very expensive.
But it's really
they're
cool.
in some places only. Yeah.
I did it with my son. It's outside of Disneyland in LA, and he came out of that and he literally said, "That is the coolest thing I've ever done in my whole life." And I said, "That's the second coolest thing I ever did."
That's good. Just bragging. Just bragging.
I've heard that space sickness is hard to predict among astronauts. Does VR help predict that at all?
Geez, I don't think we have an answer to that. It's very hard to predict. Also, people who get sick in aircraft and cars aren't necessarily the ones who feel sick in space, or aren't necessarily sicker longer in space. But that's usually a short time anyway. When you first get up there, it's not something that lasts for very long. But I don't know. I have no idea what VR in space would do.
Well, in space, I can tell you one thing for sure, that if somebody starts getting sick using VR, you better take them off. Because you could be, once you start getting sick, you could be sick for a couple hours, hours after that. So now in space, we haven't heard anything.
No one's had any problems.
Yeah, nobody had any problem. Of course, it all has to do with how long do you use it. And when you're used to this kind of environments, it's easier to support to do. So.
That's a good question.
Yeah, good question.
Any other questions? You guys have been here long enough?
Yes, well, thank you. Thank you, everybody.
Thank you very much.
Yeah,
Okay.
thank you for coming.
Okay.
Thank you so much. Yeah, that was awesome. And I have a gift.